So I'm Kartik Sondhi. I come from University of Florida, Go Gators. I'll be talking about the Airbrushed Dipole RF strain sensor antenna on polyurethane substrate, mainly called TPU. The people who worked with me on this project was an undergrad student and another PhD student in my lab, Jacob Amontree and Seahee Hwangbo. Sai is a person working at Jabil. He is working with us. He was also working with us on this project. And then Dr. Yoon, Dr. Nishida, who's my advisor, and Dr. Hugh fan. So I'll be talking about the motivation, some methodology which we use, results, and the summary. So to give you a brief idea of the university where I come from and our research group, it's called IMG, Interdisciplinary Microsystems Group. It's a 25-year-old research group. This is a photo of 23-year-old back. I'm sorry, I'm not able to point. So that photo is around 23-year-old back. The leftmost person is my advisor, Dr. Nishida. He used to smile a lot that time. Now he doesn't smile. Uh, this is the photo on the bottom right. This is our group, how it looks like right now. So to give you a motivation of why we did this, mainly my research is on printed electronics, printed flexible electronics, and one of the applications which we wanted to concentrate on, we are actually concentrating on several applications right now. We are working on wireless power transfer coils, flexible antennas. We are also trying to develop some sensor nodes for temperature sensing. But antennas was one of the primary things which we submitted to IEEE sensors. And the reason why there's several flexible antennas which are available today. It's not something out of the blue. It has been going on since last, I think, 10, 15 years. People have been working on flexible antennas. What is the issue? Why is it not so readily available? First of all, it's not so easy to commercialize it. The main reason being that it's not so environmentally stable. Usually these products die out or they age in an year or two. And we have just recently published a paper on aging properties also of these antennas. Another big problem with these thin substrates is that they have a very a low or a negative gain, which causes the antenna to be lossy and have a very low range. There are methods to make the or increase the range. That's a separate point. Uh, what's the benefits of these kind of antennas and what are the applications? Firstly, military and active sensing, health monitoring, underwater wireless power transfer. As I said, this is something else which we are working on. And in that, we're actually using coils and not the dipole antenna, which I'm going to present. So what you can see on the top left are the three images of the antennas which we made. So first of all, I'm not going to disclose the substrates mainly because the substrates which we are using are under NDA, so I cannot talk much about that. But they're basically simple polyurethane substrates. We use PE872 ink. For those of you who work on printed electronics, it's ink from DuPont. Uh, we dilated to a certain concentration, and one of the combinations which we used was 19.6%, because when you're actually airbrushing and when you're screen printing, you need to use different viscosities. And for our airbrushing thing, we found out that the best concentration is 19.6%. So that was used for the fabrication of this antenna. And before we go and think about, okay, let's fabricate an antenna, a very important parameter is that we need to do an HFSS design, which is how you're going to design the antenna. And so we used a simulation tool, which was mainly done by the RF expert in our lab, Seahee. So in that, the properties which we had to input were the relative permittivity and the dielectric loss tangent. We have an ASTM D3380 equipment in our lab, which calculates the dielectric loss tangent and the relative permittivity. Since these substrates were purchased and obtained from a different company, they did not disclose to us the dielectric loss tangent permittivity. So we had to calculate it ourselves. After that, other properties which need to be inputted into the HFSS model are the conductivity of silver. Since we're diluting the silver, the concentration as I said, we diluted the ink, the conductivity changes because now in the same area, the sheet resistance is different. Moreover, since we are again diluting the ink and we're airbrushing it, the thickness of the silver would change. Hence, these properties need to be taken into account for HFSS design. And it's very important because when we are trying to airbrush the silver, for example, if we are doing 2 or 3 coats, the thickness would be around 10 or 6 microns. For the screen printing, it's always depending on the screen of the mesh which we use. We usually use a 325 stainless steel mesh to print these things, and the average thickness is around 12 or 15 micron. depending on the emulsion thickness of the screen. So there were a lot of different parameters and which we had to take into account, and that's why these antennas, which you are seeing over here, have similar thickness, have the more or less similar resistance, and that's why for our airbrush the antenna, we had to coat 3 times. The screen printing was just done once. So whenever we're trying to do some experiments, there are always some hurdles which come in the way. One of the first things was when we had actually started making these antennas, one of the things was a testing part. For testing, we have a Mark 10 strain sensor in lab, but the big issue with that is it's completely metallic. And thus, when we are trying to measure some RF properties from it, we have a lot of extra additional noise, which we cannot take into account. Thus, we had to make our own setup for calculating the antenna. I'm sorry, to calculate the RF characteristics. So what we had to do is we had to make our own lean actuator. We grounded that. We made a movable clamp, a static clamp, and we were stretching it for 100 cycles, 1,000 cycles, 10,000 cycles, and so on. So once this problem was solved, we had to, for solving the other things which we had to do is we had to ground the whole system. We had to put it in a complete enclosed cage so that there is no additional noise from the outside. Once this was solved, the second thing came into picture, which is the particle size difference. When we are talking about 2 or 3 different inks, each of these inks are made with different silver particle sizes. Some of the particle sizes around 5 micron, some of them have a particle size around 3 micron, and some of them are even lower. They would be like a nanoparticle ink. In my case, what you can see in this is the same images of 2 different inks which we use. CA-1036 is an ink from a company called EMS, Engineering Metal, Engineering, I'm sorry, I forgot the full name. PE872 is a ink from, as I said, from DuPont. PE872 has a lower resistance. CI-1036 has a better conductivity and higher resistance in this case. And another thing is the particle size is way much bigger to what you can see in the PE compared to PE872. So one of the things which came into the picture was the surface roughness. And why surface roughness important? Because if you have a higher surface roughness, you will get a higher skin depth effect at very high frequencies. So for doing that, we had to do some calendaring and we had to reduce the surface roughness. So that was another thing. And continuing with the surface roughness, this is another paper which we had communicated and accepted in a conference called WISE, which is on reliability of antennas. And we made another antenna for 4.5 gigahertz. That's also a dipole antenna, but that's on PDMS. And since we are using PDMS, we have a different substrate, and we have a completely different design, completely different thickness, line width, so on. In that case, what happened is when we were trying to airbrush, the thickness, the surface roughness was higher. And what you can see in this graph, that at the lower frequencies, the skin depth effect is higher. Because of which, something which happened is that the surface roughness for our airbrushed antennas was around 1 or 2 microns, and for the screen printed antennas was lower. So, I'm sorry, for the airbrush antennas was around 6 microns, and our screen printed antennas was around 4 microns. Due to which, what happened is as I said, we had a very high surface roughness effect. There were a lot of losses. We had to do a lot of calendaring, which is a process in which you're taking a heat press, you're pressing the substrate to smoothen out the whole printed antenna. And once that was done, we could reduce the surface roughness and we could actually use it for our application. So some of the initial results are, one of the first things is the reflection coefficient, or the S11 parameter. In this case, so what you can see in this graph is the 3 airbrush, the screen printed the screen printed is with the CA-1036 ink. The B is the PE872 ink, and the A is the diluted PE872 ink. So one of the first things which you will notice is that for the C, which is the CI-1036 ink, that it has a slightly lower resonant frequency. And that actually happened because the substrate which we were using for this case had a higher relative permittivity. And as we know that it is indirectly related to it's proportional to 1 by root over of epsilon. So we had a lower resonant frequency. And what you can see on the right hand side is the E field radiation pattern. It was supposed to be completely circular, but in dipole antennas and very thin dipole antennas, it would not be perfectly circular. And this is something which we are still trying to understand. Mainly, another problem which happened in this case was that it had a negative gain, which was something which we did not expect. But then again, it's a very thin antenna, should be having a high loss, and that's why we thought that these results were right. One of the things which we did next, and which we are still working on right now, is trying to actually experimentally verify the simulated pattern which we had got. To continue, this is a cycling effect of antennas. What we did is we cycled the antennas 10 times using the same equipment which I showed you some time back. Uh, we cycled it 100 times. What you can see, what you're seeing on the right hand side is the after cycling effect, and we saw a continuous reduction of the resonant frequency with strain, and that was expected because it's an RF strain sensor. So one of the things which we were not expecting earlier was that the airbrushed antennas had a higher particle interparticle distance, because of which it's interesting to note that the the resonant frequency drop is much faster because the conductivity is dropping way much faster because the interparticle distance is much higher. Because of which we had a very fast drop of resonant frequency, and thus when we try to calculate the strain sensor characteristic, which is the change in resonant frequency per the percentage of strain, we saw a very high sensitivity of the RF strain sensor, airbrush RF strain sensor, because of which we could say, okay, it's better than the other existing strain sensors. And I'll be talking about that a little later. Another thing is that, as I said, we also did some reliability studies of the temperature. What you're seeing on the right hand side is a low temperature effect and the high temperature effect. We have also studied different shapes of antennas: serpentine, straight, wavy, and then we are also trying to study a design in which we can make it much. You can have a dipole and then a serpentine antenna attached with it, but that's a separate thing. For now, to summarize everything, I presented a novel design. One of the main things which I felt was important was the last point, which is that we have a 20.55% higher strain sensitivity to what has already been published till now. And the most recent publication I saw for the printed strain sensor antenna was in 2016. So that is how we are trying to base our research output on this. So the proposed future task is we want to understand physics in much more details, study the effect of particle size distribution, and strategize into trying to patent this idea. That's all. Thank you.